Hey, this is an introduction to forces and Newton's laws. So first of all, the main ideas are, what are forces? They're pushes or pulls on objects. What do they cause? They cause the motion of an object to change or the object to accelerate. If there is no net force on an object, that is, if the forces cancel, the object is in translational equilibrium and it will not accelerate, it goes at a constant velocity. We can use free body diagrams, which are diagrams of all the forces acting on an object, to figure out the forces that are acting on an object and to figure out how an object will accelerate. And we also can discuss a few individual forces. So first of all, we need to introduce the concept of inertia. It doesn't have a variable, it's a constant, but mass is related to inertia, so maybe we could talk about m. Inertia is the idea that, well, what happens to an object when there are no forces acting on it? So if you're in deep space and you throw a bowling ball, what's it going to do? Well, it's going to be moving, and what is there going to be to stop it? Nothing. Nothing will stop it. There's no friction, there's no gravity to stop it, so it's going to keep going. Same thing if you slide a hockey puck on very slippery ice, it tends to keep going, going, going. It might slow down a little bit because there is still friction, but it tends to keep going until it hits a wall or something stops it. So the idea of inertia is in the absence of forces, or in the absence of a net force, objects keep going at a constant velocity. And this is Newton's first law of motion. An object that is in motion stays in motion in its current state, and an object that is at rest stays at rest in its current state unless acted upon by an external net force. So if there's no net force, you stay at a constant velocity. Whether it's at rest or already moving, it will continue being at rest or already moving. The only reason objects slow down to a stop is because there's some net force to slow them down, whether it's friction or bumping into a wall or someone catching a ball. So that's inertia. I already said that mass is related to inertia because we can think of mass as resistance to change in velocity or resistance to acceleration. So mass is a measurement of inertia. The more kilograms an object has, the harder it is to change its motion. More massive objects are going to be harder to accelerate. The same amount of force, you'll get less of an acceleration. So if you're on a car versus a bike, if a car drives through a fence at 10 miles an hour, it's going to keep going. That fence is going to apply a force to it, but it's not going to slow down much. If you ride into a fence on a bike, your bike is going to be stopped because that same force applies a much greater acceleration. One thing that's really important, though, is mass is not weight. Mass is inertia, and it's measured in kilograms. Weight is the force of gravity. Force of gravity. And so it's measured in the units of force. So what is a force? We've already said that a force is a push or a pull on an object. Any push or a pull is a force. If you push or pull on something, you're going to try to move it. You're going to try to change its motion, stop it, speed it up, change its direction. Since a force is a push or a pull, it's in a particular direction. It is a vector. We use the letter F for force. And the units of force are newtons. 1 Newton is equal to a kilogram times a meter per second squared. So it's a unit of mass times a unit of acceleration is 1 unit of force. From Newton's first law, when there is no net force on an object, it's not going to accelerate. It's going to go at a constant velocity. And we call that state translational equilibrium. All the force vectors cancel, if there are any, or there are no force vectors on it. And so we get a constant velocity or no acceleration. On the other hand, if there is a net force, if the net force is not zero, the total force, then the object will accelerate or change its velocity in the direction that the net force is pointing. That by net force, I mean the total of all the forces added up like vectors. Now, this doesn't mean the object is moving in that direction. For example, something slowing down due to friction. It might be moving to the right, but it's slowing down. The force on it is to the left, and so it's going to slow down. The acceleration is to the left in that case. Free body diagrams are how we diagram forces, and they're really just vector diagrams. What they do is they show all of the forces acting on an object, and we label them clearly. how do we make a free body diagram? We first of all sketch out a diagram of the object, maybe on the surface that it's on if the angle matters, and we want to identify all forces acting and label those forces as vectors, aka arrows. The length of the vector is going to be proportional to the magnitude, and the direction is the direction. Note that these diagrams are only for the forces acting on an object. We don't put the velocities or the accelerations in a free body diagram because they're not forces. Free body diagrams are all about identifying the forces. Sometimes acceleration and velocity are useful. We might want to know what direction the object is accelerating or the direction the object's moving, because sometimes forces depend on that. But we don't want to put that on the free body diagram. So on the right here, we have a free body diagram for a block sliding down a ramp to the right. And how do we identify the forces acting on the object? Well, the most straightforward thing to do is think about what is the object touching, because almost all forces involve touch. In fact, all forces except for gravity, magnetism, and electricity, the object has to be touching something. So this is a block at rest on the surface here. There are three forces acting. Well, one, gravity's acting, and gravity's always pulling down, and we label that mg, or you could also label it the force of gravity, F sub g. There's also a force from the surface, because the slope here is preventing the object from going down. So there's going to be a force that surface pushes up perpendicular to that surface. We call it the normal force. And it's going down the slope, so I'm going to label a velocity vector here off to the side. But if it's going down the slope, it says there's friction acting. Friction is always going to try and slow the object down. It's going to resist sliding. So friction is going to point to the left. And it's labeled Fk for kinetic friction, but we could also just label it F sub F for friction. Let's just label it F sub F for now. So this is the basics of forces and free body diagrams. Bye.